Hello and welcome to this episode of the Industrial Engineering Notebook. Today's topic is linear optimization problems. And in this video, we're going to go over how to define those problems. There are 3 super exciting steps to that. And then we're going to solve a basic case. Linear optimization is a huge field in mathematics, and it comes up all the time in manufacturing. So I hope this video will be a good introduction for you. So let's say you're analyzing 2 machines. Machine 1 produces 50 pounds per hour, machine 2 produces 30 pounds per hour, and each machine is scrapping pounds at the same time. And it looks like we got roughly 23% of what goes into machine 1 being scrapped, and roughly 14% of what goes into machine 2 being scrapped. And you can check the math yourself. Let's say in a day you want to produce at least 1,000 pounds of material on these machines. And in a day, you don't want to scrap more than 250 pounds. And that'll keep your scrap rate at under 20%, which would be great. The other thing we got to think about, though, is cost. We want to minimize the cost of running these machines. It costs $45 per hour to run machine 1 and $60 per hour to run machine 2. So we want to minimize cost. We need to produce at least 1,000 pounds, scrap no more than 250 pounds. All of this points to the big question, how many hours do we run each machine in a day? And this is a classic linear optimization problem, tons of things going on, but there is an answer that we can come to. Step number 1 is to define our variables. These are sometimes called decision variables, and it's the thing that we want to solve for. So x1 can be the hours we run machine 1, and x2 can be the hours machine 2 runs. Step 2 is to write constraints. First, we have some positivity constraints. It's not possible to run either machine for negative hours, so x1 and x2 need to be greater than or equal to 0. And we're only concerned with 1 day, so that means x1 and x2 both need to be less than or equal to 24 hours. Additionally, we have a constraint because of scrap. There's only so much scrap that we can produce. No more than 250 pounds. And we're going to get 15 pounds of scrap for every hour we run machine 1, and 5 pounds of scrap for every hour we run machine 2. So another way to write that, 15x1 plus 5x2 needs to be less than or equal to 250. We also have a production constraint. There's a minimum amount that we need to produce, at least 1,000 pounds. And we're going to get 50 pounds for every hour we run machine 1 and 30 pounds for every hour we run machine 2. So we would write 50x1 plus 30x2 needs to be greater than or equal to 1,000. And the last factor to consider is money. We would like to minimize the cost of running each of these machines. $45 for every hour we run machine 1, $60 for every hour we run machine 2. So this third step is just defining the objective. And we would write this as minimize the total cost, which we'll define as z, and z is going to equal 45x1 plus 60x2. Okay, so we've taken a word problem with pictures and stuff and turned it into math. Now, how do we use this math to solve the problem? We want to know what x1 and x2 ought to equal. And to do that, we're going to look at a graph of x1 and x2 and plot these equations on that graph here from our constraints, and then we'll go from there. So we have x1 on this axis and x2 on this axis. x2 needs to be less than 24, so we'll consider everything below this line. x1 needs to be less than 24, so we consider everything to the left of this line. If you plot our production constraint, you get a line that looks like this. And remember, we need something greater than or equal to 1,000 pounds, so we only want to consider points above this line. Plot our scrap constraint, you get a line that looks like this, and scrap was no more than 250 pounds, so we need everything on the left or kind of the bottom to the left of this line. These are the values of x1 and x2 that meet our constraints. Every other point on the plane violates one of our constraints. And then all that's left is to minimize cost. So which point in this little triangle is going to give us the lowest cost? And the trick here is to look at the extreme points, so these kind of corners here. Here are the coordinates for each of those points. And if you remember our cost function, what we're going to do is plug each of these points into our cost function and see which one gives us the lowest cost. And looking at these costs, we can see that the optimal solution would be to run each machine for 12.5 hours each in a day. And this answer may not have been intuitive at the beginning. I think most factories would look at this scenario and say, okay, the percent that machine 2 scraps is much lower than machine 1. So we just need to run machine 2 all day and run a little bit of machine 1. We can hit this target of 20% scrap. But you, being the industrial engineer in your factory, can kind of investigate this a little bit more and see if there's a better way. And it turns out that by running each of these machines for 12.5 hours each in a day, you can hit this 20% scrap rate, produce your 1,000 pounds, and minimize your cost. If you like this video, go ahead and hit the like button. If you want to see more videos like this, well, I'll keep making them, but you got to hit that subscribe button. And if you have questions, I am happy to answer them. Just put them in the comments. Thanks.